For years, astronomers have been mystified by an unusual haze of gamma rays shining from the Milky Way's core, a puzzle known as the galactic center excess. Some researchers argue it's the combined glow of countless undetected millisecond pulsars, while others claim it may be the long-awaited signature of dark matter annihilation. Now, new simulations from the Leibniz Institute for Astrophysics in Potsdam hint that the galaxy's inner dark matter distribution may not be spherical after all, but distinctly box-shaped. And that geometric twist could put dark matter right back in the running. In this video, we'll explore what this finding really means. Let's dive in. Back in 2009, NASA's Fermi Gamma Ray Space Telescope revealed something unexpected: an intense concentration of high-energy gamma rays pouring out of the Milky Way's central region. The luminosity far exceeded what theoretical models predicted and couldn't be cleanly traced to supernova remnants, black hole activity, or any catalogued astrophysical sources. This unexplained radiation became known as the GCE, or Galactic Center Excess. Two leading explanations quickly emerged. The first involved millisecond pulsars, extremely dense, rapidly spinning neutron stars that fire narrow beams of gamma rays hundreds of times each second. If thousands of these compact objects were buried in the galactic bulge, their combined output could account for the mysterious glow Fermi detected. The second hypothesis pointed to dark matter. If dark matter particles, possibly WIMPs, or weakly interacting massive particles, collide and annihilate, they might release bursts of gamma radiation. Such a detection would provide the first convincing indirect evidence of dark matter's particle nature, a revolutionary moment in physics. For years, the shape of the glow seemed to favor the pulsar interpretation. The gamma ray emission looked lopsided and box-like, much like the distribution of stars in the galactic bulge. Dark matter, in contrast, had long been modeled as forming almost perfectly smooth spherical halos, making its geometry look inconsistent with the data. A team led by Maurice Moreau at the Leibniz Institute decided to revisit this assumption using the Hestia simulation suite, a set of high-resolution, cosmologically grounded models of the local universe. By generating a digital Milky Way analog and tracking its evolution through mergers, tidal interactions, and gravitational disturbances, the researchers discovered that dark matter halos need not remain spherical over billions of years. Instead, they can be stretched, warped, and sculpted into triaxial or even box-shaped structures near the center. When the team simulated gamma ray emission from this distorted halo, the resulting pattern reproduced Fermi's observations just as well as the pulsar scenario. In other words, halo morphology, once a key argument against dark matter, no longer automatically excludes it. This work matters because the geometry of the GCE has been one of the strongest pieces of evidence supporting the pulsar explanation for over a decade. Astronomers had argued that a box-shaped excess meant pulsars, while a spherical glow pointed to dark matter. But the new results challenge that binary rule. Galaxies are not static. They are shaped by collisions, gas inflows, star formation, and the gravitational pull of satellites. These processes can distort stars and dark matter alike. The Hestia simulations reveal that the Milky Way's inner dark matter halo may reflect this turbulent history rather than any simple symmetric model. This shift reframes the debate. The dominant question is no longer the shape of the glow, but its origin. The pulsar hypothesis remains fully viable. Millisecond pulsars are known gamma ray emitters, and the dense, dust-choked galactic center could easily hide thousands of them from view. Yet, observing individual sources there is notoriously difficult. Radio and optical signals are heavily obscured. Meanwhile, the dark matter interpretation gains renewed legitimacy. If dark matter can assume non-spherical profiles while producing the observed gamma-ray signature, the theory remains a serious contender. Confirming it would reshape cosmology and particle physics. But such a claim must be consistent with other constraints: cosmic microwave background measurements, galaxy cluster studies, gravitational lensing behavior, and laboratory dark matter searches. This study also highlights the growing importance of realistic cosmological simulations. Older models relied on idealized geometries, but modern simulations like Hestia incorporate the messy, chaotic nature of galactic evolution. That complexity may help explain not only the GCE, but other oddities in galaxy dynamics. Ultimately, the results don't prove either hypothesis correct. They simply show that eliminating dark matter based solely on morphology was too simplistic. Both ideas now stand on roughly equal ground. If dark matter annihilation can generate a box-shaped glow, the implications stretch far beyond the Milky Way. It means researchers can no longer rely on the shape of an emission region to distinguish conventional astrophysics from exotic particle physics. Instead, scientists must look to more detailed diagnostics, such as the energy spectrum of the gamma rays, subtle time variations, or correlations with known stellar populations. For those hunting dark matter, this reopening of the argument is exciting. The galactic center remains the most promising place to search, since it's rich in both ordinary matter and deep gravitational potential wells that could gather dark matter particles. Still, only upcoming observations can decide whether the excess comes from pulsars or particle annihilation. That decisive data will likely come from the Cherenkov Telescope Array, or CTA, expected to begin operations around 2028. CTA's sensitivity will far surpass that of Fermi, resolving gamma-ray sources at much finer scales. If the excess breaks into many tiny point sources, millisecond pulsars will almost certainly be confirmed. If the glow remains smooth and extended, the dark matter hypothesis will take the lead again. A box-shaped dark matter halo would also influence stellar orbits, satellite galaxy behavior, and gravitational lensing predictions. This realization may push astronomers to re-examine other galaxies showing similarly asymmetric central features. Equally important, the AIP team emphasizes that simulations are not proof. They reveal what is possible, not what is true. The next steps involve comparing the predictions to observations across the electromagnetic spectrum, from gamma rays to X-rays and infrared. Missions such as ESA's Athena X-ray Observatory and NASA's upcoming Nancy Grace Roman Space Telescope could provide crucial data on how matter and energy are arranged in the Milky Way's core. If future observations confirm dark matter annihilation, it would be one of the most profound breakthroughs of the century, a direct glimpse into the substance that makes up most of the universe's mass. If instead, the glow is traced to a vast, hidden population of millisecond pulsars, that would also be transformative, revealing a previously unseen component of our galaxy's energy ecosystem. And it's possible that both mechanisms contribute simultaneously, a mixed origin shaped by billions of years of galactic evolution. The Milky Way's center may not be spherical, but box-shaped, reshaping how scientists think about dark matter and the gamma-ray excess. This discovery doesn't solve the mystery, but it reopens it, placing dark matter and pulsars back on equal footing. As new observatories come online, we may finally uncover the true engine behind our galaxy's enigmatic glow. And with that, our journey to the heart of the Milky Way comes to an end. For now, the universe is full of surprises, and each discovery brings us one step closer to understanding the invisible forces shaping everything we see. If you enjoyed this deep dive into cosmic mysteries, don't forget to like, subscribe, and share. It helps the channel reach more curious minds. Thanks for watching, stay curious, and until next time, keep looking up.